Thanks. So my name is Ben Bartlett. I'm a PhD candidate in applied physics at Stanford in Shanwei Fan's group. And today I'm going to talk about my research designing nanophotonic processors for machine learning and quantum computing. So I divided this talk into three parts. In part one, I'll talk about how to design nanophotonic processors that can do machine learning using light. In part two, I'll talk about how to do quantum machine learning using light. And in part three, I'll talk about how to do quantum computing and quantum machine learning using minimal physical resources. So let's jump right into part one, which is machine learning using light. If you look under the hood of any machine learning model, most of the computational load is just a lot of matrix multiplication. And this uses a lot of energy. And the hardware running the machine learning model, your CPU and GPU clock speed is limited to gigahertz scales by a lot of heat. But what if I told you that we can do matrix multiplication with optics using almost zero energy and clocked over 100 times faster than with electronic CPUs? This sounds like a pretty grand claim, but we actually do optical matrix multiplication all the time. If you have two modes of light, A and B, and you run them through a beam splitter, then you effectively multiply them by this beam splitter matrix, this 1I1. So your output modes get mixed by this matrix. And similarly, if you have two waveguides, and then on one of the waveguides you put a phase shifter that shifts by phi, then you multiply by this diagonal e to the I phi matrix. But what if we want more parameters? Well, you can put two beam splitters and two phase shifters together to create something called a Mach-Zehnder interferometer, or MZI. And an MZI is basically just an adjustable valve for light. If you have two input and output waveguides, then you can adjust how much light from the top waveguide ends in the bottom waveguide and how much from the bottom ends up in the top waveguide. And this can implement any U2 or two-dimensional unitary operator up to input phases with a suitable choice of theta and phi. So by changing what your phase shifts are, you can change what the matrix is that you implement. But what if we want more parameters? Well, then you can put a bunch of MZIs together into a lattice. And this can, if you have n times n minus 1 over 2 MZIs, then you can actually implement any n-dimensional unitary matrix. And by sequentially programming each of the local interactions between the neighboring MZIs, or between the neighboring waveguides at each MZI, you can tell the entire structure to implement any unitary transformation on the input optical modes. And if you combine two of these unitary matrices together with optical gain or an attenuation layer in between, then you can actually do any matrix via singular value decomposition. So basically what you have is an optical structure that is a physical implementation of a matrix operator. And these have actually been fabricated before. This is a this is a microscope image of a photonic structure that was fabricated for a pretty famous Nature Photonics paper a couple of years ago. So in this case, if you take a bunch of these matrix multiplication layers together and you stick them between some sort of activation layers, then you can create an optical neural network, or an ONN. And in this case, your machine learning model is actually a trainable physical device where the trainable parameters are the phase shifter voltages. And you can also do the activation functions with optics as well. And this is actually something that our group has been working on quite a lot recently, is creating these electro-optic nonlinear activation functions. And we recently published a paper training a simulated optical neural network on an MNIST dataset using this type of electro-optic activation function. But we actually went a little bit further than just simulations. We actually built one. We worked with a photonics company in Texas called GenXCom, and we fabricated a small optical neural network with electro-optic activation functions built in silicon, and then trained it on the same data set. So one of the coolest things about optical neural networks is that you can train them using physical measurements. So in a standard machine learning model, when you train your neural network using backpropagation, what you do is at each iteration, you compute the loss gradient. So basically the derivative of how much your loss function changes with respect to each of the parameters in your model. And then you go through and just change all of them accordingly and go to the next iteration of gradient descent. But this is pretty computationally expensive. In an optical neural network, you can actually get the gradient information and the derivative of your loss function using physical interference measurements by interfering forward and backward propagating light on the chip. And what this means is that if you have one of these optical neural network chips with a bunch of phase shifters on it, you can literally just run back propagation and set a camera above the chip. And then if you look at how much light is at each phase shifter, the light intensity at each phase shifter will directly tell you how much each phase shifter needs to be adjusted for the next step of gradient descent. And this animation to the right is simulating doing exactly that. So we've got a 3-layer optical neural network shown in the gray panels. And then what it's trying to do is do this simple like red, blue dot planar classification problem. And the light intensity in each of the waveguides is shown by the color. And then what we're doing is we're actually training the simulated model by actually simulating how the fields interfere at each phase shifter, and then using that to obtain the gradient information. So this method actually works. And if you're interested in this, our group has an open source Python simulation framework for optical neural networks called Neuroptica, which is available on GitHub. It makes it very easy to put together a big optical neural network simulation by just throwing together Keras-style layers, and then it takes care of all of the physics simulation for you behind the scenes. So around this time, all of this unitary matrix stuff might sound familiar. We've got a phase-shifted NZI can do a unitary matrix, and you put them together, and you can do a big unitary matrix. And then you multiply a whole bunch of big unitaries together to do a computation. So this might remind you of something. And maybe optical neural networks could do quantum computing too. But how do you take this chip with a bunch of phase shifters on it and make it work for quantum information? Well, that's the subject of part 2 of my talk, which is quantum machine learning using light. So there's a lot of reasons that photonics is a great substrate for quantum information processing. Photons have long coherence times. They're easily isolated from the environment. You can run photonic systems at room temperature operation. You can make extra photonic qubits on demand. And photons are optimal information carriers between distant nodes in a quantum network. There are some surmountable scalability problems. Problem 1 is that in a photonic system, the gates are distinct physical systems. So instead of, for example, hitting an atomic qubit with several timed laser pulses to implement gates, you have to run photons through a physical structure. This means that unless you're clever about it, the size of your machine scales with the size of the quantum circuit that you want to implement, which can make very large, complex quantum circuits prohibitively large to implement using traditional free space optics. And problem 2 is that photons don't readily interact with each other because they're bosons. So implementing multi-photon quantum gates is a challenge. So returning back to our idea of how do we make optical neural networks more quantum-y? Well, idea number 1 is you could just encode your quantum state with the spatial modes of a normal laser. So if you have a 3-qubit state, you could have 8 waveguides, and how much of the state is in 0, 0, 1 is just how much of the light intensity is in the second waveguide. The disadvantage is there's not really anything quantum about this. If you have n qubits, you need a device with 2 to the n number of waveguides. So if you want a 50-qubit device, you need a photonic chip that is bigger than the sun. So this is not very useful. Idea number 2 is that you can use single photon pulses as qubits. Single photons are quantum-y, and you can entangle and interact them. And you can, with this method, you could do 2 photon gates using the measurement operation itself as the nonlinearity with post-selection. Now, this is a good idea, and there's a lot of very smart people trying to make this work, but a huge disadvantage of this approach is that it's non-deterministic. So your 2-photon gate will only work 25% of the time. This complicates the design of the chip by necessitating on-chip photon storage, and it imposes massive resource overheads if you want fault-tolerant operation. So is there a way that we can make our optical neural network implementation quantum-y while still making it spatially efficient and deterministic? And turns out the answer is yes. Our solution is a device which we call a quantum programmable gate array, or QPGA for short. This is an architecture for an integrated photonic circuit, which can be dynamically reprogrammed to implement any photonic quantum state or operator without hardware modifications. The design is spatially efficient, so if you have an n-qubit state, you only need 2n number of waveguides. It's deterministic. The success chance of the gate is limited only by the quality of the experimental implementation, and it's compact because it's a nanophotonic circuit, so you can fit a really big quantum circuit on a small chip. A schematic of the architecture is shown here. The physical layout for a 4-qubit QPGA is shown in panel A, and the corresponding logical quantum circuit is shown in B. The architecture is basically a lattice of programmable optical cells, which are similar to an MZI. And one of these is depicted in panel C. And the energy structure of these embedded quantum emitters that we've put into the chip is shown in D. And I'll talk about more of how each of this works over the next couple of slides. So in this device, qubits are encoded as temporally separated single photon pulses, which you just sequentially inject into the inputs of the device. The qubits are path encoded by the photon number within each pair of waveguides. So the basis states, whether each qubit is 0 or 1, correspond to whether the photon is in the top or bottom waveguide of each pair. Importantly, the photon number within each pair of waveguides is conserved. So photons can alter the phase of other photons with nearest neighbor interactions, but they don't ever cross over into their waveguides. So at any point in this device, the total photon number in a pair of waveguides, which collectively represents a qubit, is exactly 1. So the general strategy of this device is we can represent any quantum circuit by decomposing it into a bunch of single qubit gates that are implemented by MZIs and CZ interactions, which are implemented by scattering cells. And a CZ is just a controlled pi phase shift. So basically, photon number 2 gets a pi phase shift conditional on the state of photon number 1 being in the 1 state. Single qubit operations in this device are implemented with phase-shifted MZIs. If you recall from the previous part of this talk, an MZI with 4 phase shifters can implement any U2 operator. So the total transfer matrix of the MZI takes the form here. And using a suitable choice of phase shifts, you can implement any single qubit quantum gate, such as the common ones that are shown in this table. In addition to arbitrary single qubit gates, the QPGA needs to be able to implement 2 qubit entangling operations in order to be computationally universal. And this is accomplished using nonlinear interactions between 2 photons scattering off of a pair of quantum emitters embedded within the waveguides. These quantum emitters are basically sort of artificial atoms, and they could be quantum dots, they could be diamond vacancy centers, NV centers, or many other different experimental setups. It's not particularly picky on the implementation. The basic idea behind how this CZ gate works is adapted from a 2013 paper by Zhang et al. And these atoms, I use atoms and quantum emitters interchangeably from now on. The atom has 4 energy levels, and if you scatter a photon against the 3 state of the atom, it gets a pi phase shift. So the first photon comes in and it transitions the atom from state 1 to 3, and then the second photon interacts with this modified atomic state, and whatever part of the atom is in the 3 state imparts a pi phase shift onto the photon, and whatever is in the 1 state does not. So at the end of the day, the second photon gets a pi phase shift conditional on the state of the first photon. So the gate operation works in 4 steps. So step 1 is photon A comes in and it scatters off of the atom, and it causes the state to transition from state 1 that the atom is initialized into to state 3. The second step is photon B comes in, and whatever part of the atom is in state 3, it gets a pi phase shift from, but not from the 1 state. And in each of these scattering processes, an auxiliary photon is emitted into the delay line. And then steps 3 and 4 are the auxiliary photons each return, and photon A prime comes back and retrieves photon A by time reversal symmetry, and photon B prime comes back and retrieves photon B by time reversal symmetry. So this is a little technical, but the important takeaway here is that by the end of the gate operation, photon B gets a pi phase shift conditional on the state of photon A. And this is exactly the definition of the CZ gate. So you might wonder, what does this little eta phase shifter do? And what this does is it adjusts the overlap of the spatial modes in the scattering cell, so you can toggle the interaction on or off. So if you set eta to pi over 2, then the photons will maximally mix in their spatial modes, and they'll interact with each other in the atom, and the output state is equal to CZ times the input state. But if you set eta equal to 0, then the photon in the top waveguide stays in the top waveguide, and the bottom one stays in the bottom waveguide, and they don't interact with each other. So the output state is just the input state. So you can turn the interaction on or off. So now that we've described how this physical architecture emulates the parts of a logical quantum circuit, we would like to know how to program this device. This architecture parameterizes any quantum circuit using single qubit and CZ primitives. And the programmable parameters here are the phase shifter voltages that you can set on the chip. And by programming a QPGA, I mean the process of decomposing your desired target quantum circuit into phase shifter voltages that you could then flash onto a physical device. So there is a way to exactly program a QPGA using a matrix decomposition method. This is a lot of math and kind of technical. You can read it in our paper if you're interested. But what I want to talk about here is that you can also train a QPGA just like you would an optical neural network to implement quantum operators. So to do this, what you can do is you can just toggle off half of the nearest neighbor CZ gates between qubits to create sort of this checkerboard style connectivity, where half of the CZ gates are disabled. So the transfer matrix of the system takes the form shown here, and the single qubit phase shifters are allowed to train around this fixed structure. So the optimization routine will then go and find a set of phase shifter parameters which maximizes the fidelity between the implemented operator and the target operator over a set of randomly generated training input states. So our simulations used a custom backend that we built with TensorFlow, and they're available on our group GitHub. So as a demonstration of this optimization routine, we trained a simulated model of a QPGA that works on 4 qubits and has 20 physical circuit layers to implement a quantum Fourier transform. So if you wanted to exactly create a device to analytically implement this, you would need a circuit with you'd need a device with 57 circuit layers. But just a 20-layer QPGA can actually use this sort of machine learning-based circuit optimization technique to achieve a fidelity of 99.94%. So the figure here depicts the operator that is implemented by the simulated device at various points in training, as well as the fidelity over the course of the optimization. The size of each square represents the magnitude of each of the matrix elements of the implemented operator, while the phase is denoted by the hue. So at the beginning of training, you just randomly initialize all of your phase shifters. So your operator starts off randomly initialized with very little structure. But over the course of 50 training iterations, it rapidly converges to an operator that looks just like how a quantum Fourier transform should look. As a more animated example, here's the evolution of a 5-qubit QPGA being trained to implement a 5-qubit quantum Fourier transform. Just like in the previous slide, the operator starts off randomly initialized with not a whole lot of structure to it, but it quickly converges to a high fidelity approximation of what a quantum Fourier transform should look like. So to summarize this part of the talk, we've given an architecture that is programmable optics hardware, just like you would have in an optical neural network, but this time it works on quantum information. By embedding all of these quantum emitters in the chips, we basically allow photons to conditionally flip the state of other photons, which is not something you can do in classical optics. And you can have one chip, and by making no hardware modifications, just changing what the phase shifter values are, you can reprogram the chip to do any quantum operator. Additionally, just like with optical neural networks, this chip is trainable with machine learning techniques. And oftentimes, the learned quantum circuits are much more compact than the exactly implemented one while maintaining very high fidelities. So basically, we've taken an optical neural network, we've added a lot of quantum emitters onto the chip, but now we run into the problem that quantum emitters are really hard to get right. And this brings me to part 3 of the talk, which is quantum computing with minimal resources. And here I'm going to talk about how you can make a quantum computer that has only one controllable qubit. So indistinguishable quantum emitters are really hard to fabricate, and they're really hard to get them to work well together on an integrated photonic chip. So if we want to make a really big QPGA, how can we make it using fewer quantum emitters? Well, you could reuse the quantum emitters. So how could we do that? Well, one naive approach is that we could just take one column of this lattice that is the QPGA, and we could just reuse it. So you take the outputs from this column, and then you put the photon outputs through the delay line, then you stick them back into the inputs sometime later. And then while they're in the delay line, you reconfigure the MZIs for the next column of the lattice. The disadvantage is that while we need less quantum emitters here, we still need a lot of them. So can we do better? Well, idea number 2 is we could have some sort of photon storage mechanism. So you retrieve 2 photons from storage, you can interact them with one cell of the MZI, and then you return them back to the storage. The disadvantage is this still requires 2 indistinguishable quantum emitters. Also, MZIs are pretty slow to reconfigure. So while you're reconfiguring these MZIs, the photons could be leaking out of storage or leaking out of the waveguides. And it's not really clear what photon storage would be here, and this design is still pretty complicated. So can we do better? And we can. And our solution is a paper that we just published last month on our archive called the quantum, we sort of nicknamed the quantum ring computer. And I'll talk about how this works, but the selling points are that it just needs one single controllable quantum emitter to operate. So you don't need to have indistinguishable emitters because there's only one of them. The emitter has just a 3-level energy structure instead of the 4-level energy structure that is used in the QPGA. And it turns out this is a lot simpler to experimentally fabricate. And it stores photons just by having them counterpropagate through a fiber optic ring. And this is a very simple photon storage mechanism. There's only one waveguide here, and you don't need any circulators. Additionally, it doesn't require any MZIs or slow configurable optical components to operate. And perhaps most importantly, it doesn't actually even require single photon detectors to operate, even when reading out the quantum state. And this is one of the biggest challenges that a lot of implementations for photonic quantum computing run into, is that single photon detection efficiency is not great. So this does away with that problem. So the device has 2 main parts. There's a storage ring and a scattering cell. And the storage ring is on the left. And in the storage ring, as you might have guessed, it stores the photonic qubits. And so the qubits are implemented as time-indexed, counterpropagating single photon pulses. So it's basically a bunch of photons going around in this ring, and then they're in some superposition of rotating clockwise and counterclockwise. The photons have a pulse length tau that fits within some time bin size delta t. And then if you have a fiber ring that has a length n times delta t, it allows for n photonic qubits to be stored. The computational basis, whether each photon is in the 0 state or the 1 state, is represented by the circulation direction, so whether they're clockwise or counterclockwise. The other part of the device is the scattering unit. So the scattering unit the scattering unit is how you interact photons with each other and with the atom. So the optical switches that are embedded within the storage ring can selectively retrieve photons from the storage ring by flipping open to when the appropriate time band happens, and then flipping closed again. And then the photons can go into the scattering unit, interact with this coherently controlled atom, and return back into the storage ring in their original time band. The scattering unit would be pretty simple to build experimentally. The only parts here are the waveguides, a mirror, a fixed beam splitter, a fixed phase shifter, and an atom cavity system. So really the only involved component is the coherently controlled atom cavity system, but this has been experimentally demonstrated many times before. Importantly, there's no slow active optical components like MZIs or adjustable phase shifters to reconfigure. So you can have a very fast cycle time. So let's take a closer look at how this atom cavity system works with the photonic qubits. The atom has 3 energy levels. It's got 2 ground states, G0 and G1, and a short-lived excited state, E. So when a photon goes from the storage ring into the scattering unit, the 0 component of the photon, which is represented by this purple wave, gets reflected from the mirror. And then the 1 component of the photon in magenta interacts with the atom cavity system. So if the atom is in the G0 state, then G0 to E is a transition that is far detuned from the photon frequency omega. So the photon basically doesn't see the atom, and the cavity acts like a mirror would. If the atom is in G1, then this transition is resonant with the photon frequency, so that the atom imparts a pi phase shift. So at the end of the day, the photon gets a pi phase shift from whatever part of the joint quantum state is in the 1 state and the G1 state. So it is, again, CZ between the atom and the photon. So in our device, the atom does all of the heavy lifting. It essentially allows you to perform arbitrary operations and measurements on the photonic qubits without ever directly touching them. So we never directly manipulate the photonic qubits other than directing them from the storage ring into the scattering cell. And then any quantum circuit that you want to implement on the device can be applied to the photonic qubits by compiling them into rotations that you apply just to the atom. And the operations that you apply to the atom are actually teleported onto the photonic qubits via projective measurement. So you might be asking yourself, what does this mean? And we're going to take a very brief detour into measurement-based quantum computing to figure that out. So yeah, the quantum circuit model is probably the model of quantum computing that you're most familiar with. You start with some input state psi, which is often just the 0 state, and your algorithm is encoded by a sequence of quantum gates acting on that state. And then once you've done your program, you measure the qubits of your state in your computational basis to get a classical output, which is just a bit string of zeros and ones. So in the quantum circuit model, your program is the gates that you apply. In measurement-based quantum computing, your program is the measurements that you take. So all measurement-based quantum computing programs start with this large entangled cluster state that is totally independent of the algorithm that you want to implement. And your program is encoded by a sequence of measurements that you perform in an adaptive basis. So depending on the results of previous measurements, you might measure your qubit in the X or Y or Z basis. The remarkable thing about this is that using only non-unitary measurement operations, you can actually simulate unitary operations and compile quantum circuits into a measurement-based approach. And your adaptive measurements at each point in the program basically teleport gates onto the qubits. So to understand what I mean when I say that the measurements teleport gates between qubits, let's recall the canonical version of quantum state teleportation. In this scenario, Alice and Bob share some entangled qubit pair, and Alice also has some unknown state psi that she wants to send to Bob. So to do this, she entangles psi with her ancilla qubit A, and then she measures both of them. And then she sends that information to Bob, and the result is that the state of psi is projected onto Bob's qubit B. So basically, you've taken psi and you've destroyed it, and you've projected it onto B, so you've effectively teleported it from Alice to Bob. Quantum gate teleportation is a similar idea to quantum state teleportation. You have some state psi, and you have some ancilla that is initialized to the plus state, which is just 0 plus 1 over square root of 2. You entangle psi with your ancilla using a CZ operation, and then after you've entangled it, you can act on psi with some rotation, so in this case, h times rz, and then when you measure the state of psi, this modified state gets teleported onto your ancilla qubit, including this operation that you did after you've brought these two qubits together. So the result is that this HRZ operation is effectively teleported from psi onto the ancilla. So single qubit gates are mathematically equivalent to just 3D rotations in space. So just like you can take any 3D rotation and decompose it via Euler angles into a rotation about x, and then a rotation about y, and then another rotation about x, you can do the same thing for single qubit gates. So you can actually build up an arbitrary single qubit rotation U using 3 of these teleported HRZ rotations. And in this case, the angles that you rotate the qubits by are adaptive. So the sign is going to depend on the measurement outcomes of previous measurements. And after you've done all 3 of these measurements, you've effectively built up what U is, and you've applied U from psi onto your last qubit up to some known possible Pauli error that can be deterministically canceled out. So that was our very brief intro into measurement-based quantum computing, and let's get back to the world of photonics. So we want to do measurement-based QC with photonics, but photons are not great for measuring. Even state-of-the-art single photon detection efficiency is only a little bit more than 90%. And also, if you have a photonic qubit and you measure it, it destroys the qubit, so it's not there anymore. The atom in our device is a lot more ideal candidate for measurement. You can measure an atomic state using a quantum jump technique with near 100% efficiency, and the measurement operation does not destroy the qubit. So it's still there. You can do more stuff with it later after you've measured it. So we have some arbitrary state psi, which is our photon, and we've got our ancilla, which is the atom in the device. And we would like to reverse which one we measure. So the question is, can we teleport gates by measuring the atom instead of measuring the photon? And as you might have guessed, the answer is yes. So the way that a gate teleportation works in this device is basically 3 steps. The photon gets directed from the storage ring into the scattering unit, and it scatters off the cavity. And this, as we learned, applies CZ between the photon and the atom. In step 2, the photon is returned to the storage ring, and then you apply a X rotation to the atom. And then in step 3, you measure the state of the atom, and this teleports the rotation onto the photonic qubit. So let's go more into how this works step by step. So I'm going to follow the path of the photon going through the scattering unit, and then I'm going to build up a quantum circuit as it goes. So we've got a photon that's just coming out of the storage ring. It's in the scattering unit, and some part of it is in the top waveguide, some parts in the bottom waveguide. this top rail here of the circuit, the top one represents the state of the photon, and the bottom one represents the state of the atom over here. So the photon's going into the scattering unit. It passes through the phase shifter, which applies this z pi over 4 rotation. It passes through the beam splitter, which applies a beam splitter matrix. And then it interacts with the atom cavity system. And this applies control z between the photon and the atom. Then it's coming back through. It gets reflected. It's going back the other way. Goes back through the beam splitter, picks up another beam splitter matrix, goes back through the phase shifter, and picks up another z pi over 4 matrix. And then finally, it's back in the storage ring. At this point, we apply a Rx rotation to the atomic state using a timed laser pulse, and then we're going to measure the state of the atom. So if we look at this mathematically, we start out with some arbitrary state psi n, which looks like just like this, which is all this is saying is just in some arbitrary superposition of going clockwise and counterclockwise in the ring. And then once you've done all of the operations that we just listed, going through the beam splitter in the cavity and then back through and into the storage ring, and once you measure the state, depending on the result of the measurement, whether the atom ends up in the G0 or G1 state, it projects the state of the photon to one of these two expressions. So if we simplify this to express psi out in terms of the input state, psi n, then we get that the total operation performed here looks like this. It's the same rotation that we applied to the atom, except in this case, it's going about the y-axis, y instead of about x. And then we've also got some extra rotations about z that are caused by the phase shifter and the beam splitter. So if we look at how varying the angle that we rotate the atom state by affects the state of the photon, we can see that as we rotate the state of the atom here, the state of the photon rotates by the same amount. And the only difference between these two is that whether the atom ends up in the G0 state or the G1 state means that the photon rotation angle will be offset possibly by pi. So let's take a minute to think about what this teleported gate does. The expression of the gate that it results from one pass of the photon through the scattering unit and back is shown on the left, and the corresponding action on a Bloch sphere is shown to the right. The intuition here is basically that this whole operation gives you RY of theta with some extra useful crap. So going from left to right, because we've got left matrix multiplication, we start off with this fixed rotation about z by pi over 4, and that's just going through the phase shifter. And then we've got a variable rotation about y by theta, but depending on the result of the measurement, it might overshoot this target angle by pi, and that's given by this dotted line here. And then we've got another fixed rotation about z by pi over 4 plus pi, and that's this gray line here. And the question is this teleported gate universal? Or if we think about this in our Bloch sphere picture, can we make any 3D rotation using only variable rotations about y, the Ry of theta, and fixed 90-degree rotations about z, with the caveat that these rotations might overshoot? So if we start with 3 rotations, we want to build up our target rotation u, and we have 3 different rotations, like in our Euler angles. And r here is the form of this expression that we got from the gate in the previous slide. And we start out with this sequence of 3 rotations. We do a bunch of really gross math, and at the end of the day, we find that this operator can be simplified into this form. So there's 2 parts here. The important part is that we have on the right, we've got this sequence of a y rotation, an x rotation, and another y rotation. And this gives you this sequence of y, x, and y is exactly the y-x-y parameterization of an Euler angle rotation. And then on the left side, we have some possible Pauli error term. So basically, we can do an arbitrary rotation plus some error, and then this error can actually be deterministically removed by scattering the photon against the atom that is initialized to the G0 or G1 state. So the answer is yes, this gate is universal. You can use sequences of these teleported scattering operations to build up arbitrary single qubit gates. So we can do single qubit gates, but what about 2 photon gates? And the answer here is also yes. In fact, the well-known Dwan-Kimball protocol uses a similar system of scattering against the 3-level atom to implement a CZ gate between 2 different photons, and we can just directly use that here.
So scattering the photon off of the atom applies CZ between the atom and the photon. So if we want to implement CZ between two photons, all we have to do is scatter the first photon, rotate the atom, scatter the second photon, rotate the atom back, and then scatter the first photon again. And then when we measure the state of the atom, we get that there is a CZ gate that is projected onto these two photons, along with some extra crap that we can cancel out with some additional single qubit gates. So the device can do single qubit gates, and it can do CZ, so it's universal. It can do any quantum computation. So if we want to implement any n-qubit unitary operator, we can follow a three-step circuit compilation process. First, we decompose U into single qubit gates and CZ. Second, we decompose the single qubit gates as Euler angles. And then third, we run the device and we use a classical control system to adapt the rotation angles and correct for Pauli errors as they accumulate. And just as a more concrete example, in our paper, we actually included a hand-compiled program that will implement a 3-qubit quantum Fourier transform. And this is all just a bunch of subroutines and hand-computed rotation angles. But the important part here is that all of this boils down to just 6 instructions, which correspond to opening and closing the switches, rotating the state of the atom, measuring the atom, and initializing the state of the atom. So there's no photon, like direct control of the photons here. So we can do our arbitrary quantum programs, but then at the end of the day, we want to read out the quantum state to get our classical bit string. You can do this using only atomic measurements too, because you can construct a swap gate between the photon and the atom using a sequence of 3 scattering interactions. And what this does is this allows you to measure the states of the photons using the atom as a proxy. So you don't need any single photon detection here. And you can, again, measure the state of the atom using a quantum jump technique to near 100% efficiency. So to measure out the entire photonic state, you just swap the state of photon 1 with the atom, measure the atom, swap the state of photon 2 with the atom, measure the atom, and continue until you're done. So we know how this device works now, and the experimental design of the device is quite simple, but what can we expect in the presence of real-life imperfections? So to answer this question, we sort of categorized our possible sources of error here. The first error is that you could have deformation of the input pulse after scattering against the atom. So you come in with some Gaussian photon input pulse, it scatters against the atom, it goes back into the waveguide, and now it looks a little bit different than a Gaussian. Second, you could have atomic spontaneous emission loss, where the photon interacts with the atom and then gets emitted into some mode that is outside of your cavity system because you have an imperfect cavity. Or 3, there's photon leakage from fiber attenuation and switch insertion loss. So basically, you have imperfect optical fibers or switches, and the photons can scatter out there. So to answer these questions, for the first part, the input pulse deformation, we ran a full wave simulation of the photon interacting with the atom cavity system. And under realistic assumptions of the cavity cooperativity, which is basically a measure of how good your cavity is, and your pulse length of your photon, you can get that the pulse shape infidelity is around 10 to the minus 4. For the spontaneous emission loss, under realistic assumptions of the cavity, you can get that the loss probability per cycle is around 10 to the minus 5, and the fiber attenuation and switch insertion loss come around to 10 to the minus 4. And by realistic, I mean people have demonstrated this before in some experiment that is similar to this system that we're proposing. So if you put this all together, the overall per cycle fidelity here is around 99.95% is what we could realistically expect. And the exciting part is that this value is tentatively below a high fault tolerance threshold of 10 to the minus 3. I don't want to claim that this is a fault tolerant architecture because that's a pretty involved, complicated claim, but it does certainly work with a high fidelity per cycle. And the other takeaway is that with this high fidelity, you could potentially have deep circuits that are even thousands of layers deep that could have still a fidelity above 50%, even before you apply error correction to your device. So to summarize this part of the talk, I've shown how you can design a photonic quantum computer with minimal physical resources, just one coherently controlled atom. And this one atom does all of the work.
using only operations that you apply to the atom. They can be teleported from the atom onto the photons via projective measurement. And this design is universal. It can do any quantum program. It's deterministic, so any errors can be deterministically canceled out, and your quality of your error rate per gate is determined just by the quality of your experimental implementation. And the design is robust to experimental imperfections. It's also much more experimentally feasible to make than a QPGA. So just to summarize this talk, in part 1, we talked about how you can do machine learning using light with optical neural networks. In part 2, I talked about how you can do quantum machine learning using quantum light. So you take this into single photon pulses and you add some quantum emitters and you allow the photons to conditionally flip the state of other photons. And in part 3, I talked about how you can make a QPGA from part 2 using just one single coherently controlled atom. So that's the end of my talk. Thanks for everyone's attention, and I'd love to take any questions at this time.
Juan Miguel, you're muted.
I should I should learn not to do it twice in a row. I was saying, Ben, thanks again for the fantastic talk. Wow, it was really beautiful and amazing, and you covered so many things. We have time for, there were a lot of questions because you covered many things. I would like to maybe focus on some questions related to this like single atom ring architecture for quantum computing.
Sure.
So could you, a lot of the questions, I want to try to summarize like the spirit of many questions. Could you comment a bit more on how this is implemented, right? So is this something that's done on chip? Is this something that's done on a tabletop? What kind of like elements are you using? Does this operate at room temperature? Can you just elaborate a bit more on like the experimental component of it?
Right. So the way, so if I was going to build this, we actually have thought about beginning like doing an experimental implementation of this. It's still in the early stages, but the way that I would do it is it would be a fiber optic setup, not on a chip, because having a fiber, your fiber you can make fiber with a lot lower optical attenuation than you can make waveguides, and you need a big ring to store a lot of qubits. And I would probably also have just a macroscopic atom sitting in a cavity somewhere, because that's also a lot easier to make high quality big cavities than little cavities. You could do it on a nanophotonic chip. The issue there is that is mostly that waveguide attenuation is a bit higher than fiber attenuation. But again, it's pretty agnostic to the actual implementation here. This could operate at room temperature with the possible exception of, depending on your implementation, the atom needs to be thermally isolated from the environment. So this could either mean it just is sitting in a vacuum chamber where it's not, it's not interacting with other stuff, or if it's an on-chip quantum dot, the quantum dot might need to be cold. But if you're using optical frequency photons, it doesn't need to be super, super cold. The issue with keeping a lot of quantum computers very cold is that if you're using superconductor qubits, those often operate in the microwave regime, which is much, much more sensitive to thermal noise than optics is.
Awesome. And also some questions were related to essentially I would say the size of the ring. And if you can comment more with respect to essentially how many distinguishable wave packets, or how many different photons you could actually fit in. Right.
So you basically, there's a couple of competing factors here. The higher your cavity quality factor is, then in order to get minimal pulse deformation, you need a long photon pulse. But if you have a longer photon pulse, that also means that your time bin size needs to be larger, so your ring needs to be larger. So we did a couple of sort of back of the napkin calculations for this, and if we assume a photon pulse of around a nanosecond, then you can basically have a few hundred qubits in a ring that is on the order of like 10 meters long, circulating around. And this is assuming that the time bin size is significantly larger than the pulse length.
Awesome, and thanks, Ben. And there were some questions as well regarding details of measurement-based quantum computing. Right, so I think that that's something that it's really useful to understand the fact that light doesn't just sit there, right? It's always moving. So it really requires a different way of thinking about how to process and how to transmit information. Could you comment a bit more in terms of, for example, a concrete question? If you had a circuit that would, in a circuit model, run on, say, n qubits and have some depth that's maybe linear, how does that translate in terms of like the resources required to be implemented in a measurement-based setting? How many effective qubits do you need?
It depends a lot on your experimental implementation. There was a good paper that was published a couple of years ago in PRX called something to the effect of on the fault tolerance thresholds for measurement-based quantum computing. And basically what they found is that the quality of your switch and the speed of your switch is one of the biggest important factors here in determining what types of overheads you're going to need. It's definitely not a one-to-one. So if you have 10 logical qubits, you're going to, at the very least, each operation that you're going to do on a qubit is going to remove one physical qubit from your cluster state. So the size of the cluster state that you need is going to depend on both the number of qubits that you have and also how long your program is that you're running. So more complicated circuits are going to need larger cluster states. But one of the fun things of this is that you can also generate the cluster state as you go. So as you're destroying this end of the cluster state by measuring it over here, you're also doing more entangling operations to generate more cluster states on the other end here. Exactly.
Yeah. Thanks for that. So I hope that answers some of the questions that were asked in chat. There's also a very important question from Read It Loud. That's great, but when can I buy a quantum computer for my home and have some money left for pizza?
A while. Probably not super soon. I think a lot of people are expecting that, at least with superconducting qubits, that we might reach some level of fault-tolerant scalability thresholds in the next 5 or 10 years. That's not to say that we'll immediately have, the 2 million qubits necessary to break Shor's algorithm, but we might be able to start doing some useful quantum chemistry simulations with them. I know that you've just published a paper on that. And photonics, I think, is perhaps a little bit behind superconducting qubits, but it's definitely catching up. And I think that in the long term, I'm biased because I do photonics, but I think in the long term, photonics is going to win out as the dominant hardware platform.
Yeah, there's a few entire companies that agree with that statement. Let's put it that way. I have a question for the chat very quickly. What do you think of Ben's T-shirt? Please comment. I will refrain from saying though because I'm biased myself. Ben, so we have only a few minutes, but something that we like to do in these sessions is to, just kind of have a more informal chat. So as expected, everyone was very impressed with the beautiful animations that you have. And that's something that I think distinguishes you as a scientist, at least in my mind. Would you care to share a little bit of that aspect of yourself? Why do you have that interest and where does this ability to do beautiful things? Because I know you also play the piano, if I'm not mistaken, and you paint, right? So you have a big connection with art. Could you just elaborate on that aspect of yourself?
Yeah. So if you follow me on Twitter, you know that I spend a lot of time making all these sort of science animations to explain different math or science concepts. I actually have a backup slide in my presentation with a whole bunch of them on them if you want to switch to that. But I really like sort of the fusion of art and science here. It's definitely really fun to visualize how do I take this concept and explain it in terms of something that can be more than just a static figure. So I've got all these moving images, and I have a lot of fun sort of tweaking them and trying to make them look pretty and perfect. But then it's also definitely scratches the coding itch of really liking to make these automated systems that work really well. So I've got all this extra library that I've developed in Mathematica for making all these animations. So yeah, I really like just sort of trying to get people to I think the best type of proof is a proof that you can just look at and immediately see, that's how that works. And that's kind of what I like to do in my animations is explain these science concepts in a way that people are that's
from my perspective, you really have mastered that art, right? Not perfected it, but definitely mastered it.
Yeah.
Ben, so you do a lot of theory work and a lot of work that's related to software, but if I'm not mistaken, you also work in the lab. Is that correct?
Yeah, recently I have been working in the lab a bit more. I did a bit of experimental work towards the beginning of my PhD, working in some nanofabrication and some atom interferometry experiments. And then I switched to theory. And then when COVID hit, after about like 6 months of sitting at my apartment just doing math all day, I was like, okay, this is fine, but I am going to go insane if I don't get out of my apartment. So I talked with some of my experimental friends in lab and was like, hey, I don't really know what I'm doing with experiments, but please, you got to help me. I got to get out of the house. So, now I'm working on this experiment that we're I guess I can't say too much about it, but we're basically trying to look for some interesting quantum transitions in 10 vacancy centers, and it involves a lot of fancy electron beams and really high-powered lasers, and that's definitely fun to set that up.
Excellent. And do you have any fun stories related to your adventures in the lab?
Yeah. I guess like 2 weeks ago, I had an interesting bug that I found, which is that we were looking at a spectrometer of a readout of this photoluminescence of when we hit this vacancy center with an electron beam and a photon beam at the same time. And I kept noticing that it looked fine, but then every time I went to try and take a picture of the screen, it started messing up. And I was like, well, what is going on here? And eventually I figured out that it was the IR dot projector and the Face ID camera that was interfering with the spectrometer measurement. So that was a fun thing to tell in the meeting.
I love these stories because you see all these papers that give you the experimental setup and this is how we did it, but there's all these little details of things that go wrong and like bugs to fix in an experimental side that I think are really fascinating.
Yeah, that's one of the things that I think is the best about theory. I feel very privileged as a theorist to just be like, oh, it just depends on the experimental implementation. That's the easy part. But no, it's a lot harder to actually build these things than it is to just hand wave and be like, oh, this is how you would build it. So I definitely have a lot of respect for experimentalists.
Likewise, I share that feeling completely. When you try to do something and realize how difficult it is, you gain a lot of admiration for people that actually do it.
And then there's just stuff can go wrong for like like my first rotation at Stanford when I was like, oh, maybe like AMO physics is not for me. I was building some like interferometry setup and a laser setup, and I sneezed on components, and I spent like hours going and like taking off stuff and cleaning it and then realigning it. And I was just like, oh, this is maybe not what I should be doing for most of grad school.
When are you going to graduate? I'm sorry, I sneezed on my experiment. It's going to take a bit longer.
Yeah.
Ben, thank you so much. This is time for us. This was fantastic. I don't get tired of looking at all these beautiful pictures and animations, and you really covered a lot. I always like to some photonics into the mix. So thanks again for joining and for the fantastic talk.
Yeah, thanks for having me.